Hi there and welcome to tutorial 11, which is on Core 3 Trigonometry. It's the second video in the series of Core 3 Trigonometry. As always, let's take a look at the Edexcel specification. It says that we need to know these aspects about trigonometry. In the last video, we just introduced secant, cosecant and cotangent, and we talked about how they're related to sine, cos and tan. But this video, we talked a little bit about the graphs previously, but we're going to go more into understanding the graphs and the domains of these functions. As always, we need to be able to draw the graphs in angles and radians. Okay, so let's take a look. Firstly, let's deal with the secant function. Now, secant, or sec of theta, is defined to be 1 over cos theta. So here I've drawn the cos theta graph. Here's theta along here, and the y-axis is y equals cos theta. That's what I've drawn here. So I'm just going to rub that out there. That's our y-axis. And the question is, what does sec of theta look like if cos of theta looks as so? Well, the way we can do it is we can plot 1 over the value of the cos graph at various points and see what it looks like. Let's maybe start, let's start here. Here the value of cos theta is 1. So 1 over 1 is 1. As we go down here, cos theta is getting smaller until it's a very small number indeed. 1 over a very small number is a very big number. So it might look something up there. It might be above, it looks something up there. And then we get to 0. 1 over 0 is undefined. So this is definite infinite. It's somewhere up there. Okay, right, it never reaches there. It's undefined. Here, we're 1 over a very small negative, which makes us a very big negative. Looks something like that. Here, we're at minus 1. 1 over minus 1 is minus 1. Here, 1 over a very small negative is a very big negative. So it's over here. Here, 1 over a very small positive is a very big positive. And here, 1 over 1 is 1. So you might get the impression that the graph is starting to look something like this, with a bit of light. You might imagine that if you plotted more points in there, the graph might look something like that, and it might continue onwards. So let's actually take a look at what the graph does look like. And indeed, the graph is looking kind of as we predicted. So I'm just going to rub out the bit of working we did previously here. That still is theta here. And here what we have, well, this graph here is the sec theta graph. And the graph we originally had here was the cos theta graph. So that's exactly how the graph looks like. I just want to talk a little bit more detail about some of the key features of the graph, so I'm going to do that on the next slide. That's how we generated the graph. These are some of the key features. Here's the graphs again. Now, as before, this was our cos theta graph. And here, this is our sec theta graph. Now, what's the domain of sec theta? What theta values can we put in to the function and it be defined? Well, we can put any theta value in. So theta is a member of the real, but a couple of thetas or several thetas cause us problems. Pi by 2 causes us a problem, because at pi by 2 the graph shoots off to infinity and negative infinity. There's an asymptote at pi by 2. And 3 pi by 2 causes us a problem for the exact same reasons. And back this way, negative pi by 2 causes us problems, and negative 3 pi by 2 causes us problems. So the one thing, theta can't be as follows. Theta cannot equal pi by 2 plus any multiple of pi onto it, plus some numbers of pi, a multiple of pi, where n is some whole number integer, positive or negative. So it can't be pi by 2 plus pi, it can't be pi by 2 minus pi, or pi by 2 minus 2 pi. It can't take any of those values because there the function is undefined. Sec theta is undefined. What's the range of this function? What y values can it take? Well, sec theta on the upward u's, as you could think of them, is always bigger than or equal to 1. And sec theta on the sort of negative n shapes is always less than or equal to -1. And sec theta can't take any value in between 1 and -1. Cos theta is in between 1 and -1, but sec theta is either bigger than or equal to 1 or less than or equal to -1. Some other common features, well, the asymptotes. We've already talked really about where the asymptotes lie. The asymptotes are the points at which the graph becomes undefined, and they are that theta, at the points theta, is pi by 2 plus n pi. At those values, at those lines, these are lines defined here, this function is not defined, has an asymptote. What else can we say about the function? Well, we can talk about its period. How long does it take before it repeats itself? Well, how long does it take before you have the bottom of a u here? Well, it takes you till 2 pi to get there. So the period, it repeats itself every 2 pi or 360. And lastly, we could say it's an even function. We could call it, is it odd or even? You should know what this means by core 2. It's an even function. Okay, and by that I mean, if we put, say, a positive value of theta in there, we get the same answer when we put the negative value of theta into the function. So the function, we could say, the way to write it, we could say that sec theta always gives us the same answer as sec of minus theta, the negative value of that. Now, all of this as well it is equivalent for degrees. So the domain in degrees, theta cannot be equal to 90 plus 180 times n. Same thing. And here the asymptotes would be at 90 degrees plus 180 n, and the period would have been 360 degrees. So I'm just doing it in radians because it's maybe slightly trickier, but you should be able to translate into degrees. Okay, let's look at cosecant function. The cosecant function should remember the cosec of theta is defined to be 1 over the sine of theta. And I'd encourage you just to take a minute. I've drawn the sine graph below. Could you sketch the cosec theta graph from looking at the sine graph? So just a few seconds, then I'll go through. In a similar way as to what we did before, if we plot various points of 1 over the sine graph, we end up with a cosec graph looking something as so. Okay, so the cosec graph would look something as follows. And I want to just take a second in order to highlight some key points of the cosecant graph. So here we go, the cosecant function. What's the domain? What thetas, this is theta, and this is our y value, let's say, and this here is the cosec graph. This u, this n, and this n. What's the domain? Well, what theta values can we put in? Well, we can put any theta a member of the real, apart from a couple of thetas where the function becomes undefined. The function becomes undefined at 0, at pi, and at minus pi. The function is not defined there. So theta cannot equal n pi, where n is an integer. N can be 0, 1 pi, 2 pi, minus 2 pi, etc. So they're the only numbers theta can't be. What's the range of the function? Well, the y numbers it takes are always bigger than or equal to 1 or less than or equal to minus 1. So cosec theta is always bigger than or equal to 1, or it's less than or equal to minus 1. It's not anything between 1 and minus 1. And some other features, well, the asymptotes, we've already talked about where the function's undefined. The asymptotes are at the lines theta is equal to n pi, where n is a member of the integers. N is an integer. What else can we say about this here? When does it repeat itself? What's its period? Well, its period, it repeats itself from here, minus 3 pi by 2 to pi by 2. It takes 2 pi to repeat itself. And lastly, odd or even. Is it odd or even? Well, what we see here, by symmetry, if we take a positive value of theta here, and we work out cosec of that, it actually gives us the same answer as the negative. How does that relate to negative theta, putting it in? Well, they both have the same number answer. One's positive and one's negative. The way to phrase that is if you look at cosec of negative theta, okay, it gives us the same answer, the same number answer as cosec of theta, apart from it's a negative. Okay, so it's an odd function. So in this particular case here, it's an odd function. And they're the key points of the cosecant function. Lastly, we better look at the cotangent function, or cot. As you remember, cotangent function, cot theta is defined to be equal to 1 over tan theta. And here I've drawn the tan theta graph for us. And I'd encourage you just to, for a moment, pause and think if you could draw the 1 over tan theta graph. So if you could take the reciprocal of each of the values of the tan graph here and see what the graph looks like. I'm going to show you what it looks like then. This is what it ends up looking like. Let's just have a brief discussion about why that is. Here, the graph is a very small positive number, and 1 over that is a very big positive number. Here, the graphs are 1 over a very small negative number, and 1 over that is 1 over a very big negative number. At 0, the graph's undefined up here and undefined down here. At this point here, tan theta is 1, so 1 over tan theta is also 1, and that works here, here, here. And at this point here, tan theta is minus 1, so 1 over tan theta is also minus 1. And hence the graph looks as follows. Now, as before, just want to take a few points out of this graph here. What's the domain of the graph? What x values can you put in, or what theta values even? Now, theta is a member of the reals, but what causes you problems is theta being 0, theta being pi, theta being 2 pi, theta being minus pi, and theta being minus 2 pi. So theta cannot equal any multiple of pi, n pi, where n is a whole number or an integer. What's the range of the function? Well, the y values the function takes, so anything up from infinity down to 0, down to negative infinity. So actually, cot theta is simply a member of the reals. It can take any value. And what are the other features about the graph? Well, the asymptotes, we've already mentioned the asymptotes. The asymptotes are the values where the function tends towards infinity and minus infinity, and that's theta is equal to n pi, where n is a member of the integers. Is there any odd or even going on? There's no odd or even as such going on, so don't worry so much about that. The last thing we should talk about is the period, how often it repeats itself. How often are you coming down to a root and then you're going negative? Well, the next time you're doing it is pi later, so the root is pi here. And if we were to translate into degrees, this definition here would be 180 n multiples of 180, and here the period would be 180 degrees. And they are the graphs of sec, cosec and cotangent, and you have to be familiar with them. And the last thing we should be able to do with the sec theta, cosec theta and cot theta graph is to draw various transformations of them. So I'm going to do a complicated example and leave a few for you to do yourself. Here's a question. Sketch in the interval 0 to 360 the graph of 1 plus sec 2 theta. I always start off by drawing cos theta and then the related sec theta before I start performing transformations. So cos theta looks something as so. Okay, key points here, 0, 90, 180, 270, and 360. And the sec theta graph there, we know looks something as follows. So it looks something like that. It asymptotes at 90, asymptotes at 270, and looks something like that. Okay? Then we need to think about and consider what would the graph y equals sec 2 theta look like. Well, that's a stretch. You should know these transformations. Scale factor a half in the x direction. Or you could think of it as a squash by scale factor 2. Okay, so everything, all the key points here are going to be squashed in by a factor of 2 or stretched by a factor of a half. Now it's handy here, instead of drawing the original graph from between 0 and 360, because everything's going to be squashed in by a factor of 2, if we drew the graph doubled out to 720, it's going to help us mark the key points between 0 and 360 of the squashed graph. So I'm just going to extend this a little bit so we can draw up to 720 because it's going to help me significantly. The cos graph comes back down here, goes up here and finishes over here. Okay, the key points here will be another 90 across, which would be 450. This point here would be 540. This point here would be 630. And this point here would be 720, and the corresponding cosec looks something like that, and something like that, although that should come up there and actually touch. Okay, so it helps to extend it out to 720 so I can mark the key points when I squash everything. Now, I'm going to just mark the points where the asymptotes are. There's going to be one at half of 90, which is 45. So I'm going to put that 45. There's going to be one at half of 270, which is 135. There's going to be one at half of 450, which is 225. There's going to be one at half of 630, which is 315. And the last point there is going to be 360. And we're going to have something that looks like this. We're going to start at 1, going to go up here, then we're going to have our little U shape down here, then we're going to have up here, then we're going to have down here, and lastly we're going to start up at infinity and come down to 360 as we came down to 720 here, we're going to come down here to the point 1. And that is the sec 2 theta graph. Lastly, just to finish it off totally, y equals 1 plus sec 2 theta. This adding 1 onto this ends up shifting the graph up by a unit of 1. So everything gets shifted up by a unit of 1, which makes it easy. That was 1, 0. Now it's going to be 2. This here is going to come up and touch here, this point here, asymptote up there, be shifted up 1 here, and lastly going to asymptote there. And the key points are, as before, 45, 135, 225, 315, and 360. This point here, just to make it very clear, is the point 0, 2. This point here is 45. This point here is 135. This point here is 225. This point here is 315. And lastly, 360. So, hence we have a sketch of the graph 1 plus sec 2 theta. Now I'd encourage you to have a go at these few yourself, pause the video, work through and see if you can get the right answers. Here we go. Okay, I'll quickly go through the answers for these. I'll do them one by one. Here's the A first of all. Before I draw sec 2 theta, I'm going to draw sec theta. So I'm going to draw cos looks something as follows, and we know that sec would therefore look something like this. The key points 90, 0, 90, 180, 270 and 360. And sec of 2 theta is a squash of everything by a factor of 2. So this asymptote here would no longer be at 90 but be at 45. This asymptote here would no longer be at 270 but half that 135, etc. And we'd be squashed in. So you end up getting something that looks as follows. And I've labelled each of the key maximum and minimum points there. This first asymptote here, as I said, is at 45, the next one's at 135, and if you had continued the graph it would have been 225 and 315 would be the next ones. It's very like the example I did in the first case, in the example case, other than I didn't add 1 at the very end. So there is how you would do it. Next one was cosec theta. Well, cosec comes from sine, so the sine graph looks something as follows. Okay, and 1 over the sine graph will look something, the cosec graph will look as follows, but it should touch there, and the asymptotes would have been these key points here, which would have been 180 and 360, and the minus cosec graph is the reflection of the cosec graph in the line y equals 0, or the x-axis. So it would have looked something like this. It should have looked something like this. Should have been reflection of that one, reflection of that one. So it would have looked something as follows there. And those were the key points labelled. Instead of here being at 91, it would be 90 minus 1. And instead of here being at 270 minus 1, it would have been at 270 plus 1. The next one, 1 plus sec theta. Well, the sec theta graph we've drawn several times now. The sec theta graph looks something as follows. The sec theta graph looks something as follows, where the key points here, that was 90, that was 180, that was 270, and that was 360. And 1 plus that would have everything been shifted up. So if I could shift all that up, let's see if I could shift that. I could shift, or what I could do is I could shift the axis down even. I could shift the axis up, down like that, and it would look something as follows. With that point there is 0, 2, and that point there is 180, 0. So let's see how it would have looked on here. This point here would be 0, 2. This point here would be 180, 0, etc. And last one, cosec of theta minus 30. Well, the cosec graph comes from the sine graph. Let's remember the sine graph looks something like this. So the cosec graph ends up looking something like this, where key asymptotic values are at 180 and 360. And cosec of theta minus 30, well, that's a shift 30 degrees in the positive x direction. So if I could shift all this 30 degrees in the positive x direction, so instead of this being at 180, this would now be at 210. So it would be something as follows. At this point now would be 210. That point now would be at 390, but I wouldn't care about that point. That would be half rubbed off up to that point. And we would have also been having ourselves another portion of this down here. We would have been having something along the lines of the following for a part of the graph as it was before the axis. So we have something like this. Instead of being at the point 0, instead of being at the point 90 and 1, it will be at now the point 120 and 1. And this point here, instead of being previously at the point 270 minus 1, it will be at the point 301, shifted across 30. This point here, is 0 minus 2. How could we work that point out? Well, we would stick 0 in as our theta, and we would have worked out cosec of minus 30, which would give us the answer minus 2, and hence we have those transformations. I've finished everything I wanted to say about drawing the sec theta, cosec theta and cot theta graphs. I'd encourage you to read chapter 6, page 80 and 90, work through those examples and do exercise 6b all. Then tune in for my next video. Thank you very much for watching.